too minimal. Okay, can you see that okay?
Yep.
Great. Okay, well, thank you very much, Harley, for inviting me to this colloquium talk. It's my pleasure to be giving the talk. I'm over here in the kind of the corner of England, just right by France, at the University of Kent. I thought you might like to see the map just to see where I am, where I'm dialing in from. Now, the title of this talk, Making Types More Descriptive via Grading, might be quite enigmatic at first, especially to the US audience. So students might be imagining that there's some sort of types and we give them some grade like B minus, D, A minus, or something like this. And it's not like that. When we're talking about grades, it's about gradation. So what we'll be getting onto later is the idea of being able to classify aspects of programs, properties of programs, and traditionally this might be done in a sort of binary way, it either has this property or not. And grading is all about having a sort of spectrum, a gradation of those properties to give you a bit more fine-grained information. But we'll get onto all of that in a little bit. I wanted to sort of, as this is a talk to students, I wanted to kind of contextualize what we're doing, set the scene somewhat, by going all the way back to this computer. This is the EDSAC. It was a computer that was built in Cambridge in the late 40s. It was running for about a decade, and it was the first computer in the UK that worked that people knew about, because there was computers that worked that people didn't know about for a long time, that were being made in secret by people famously like Alan Turing during the Second World War. But people knew about the EDSAC. And it's a nice place to start here with the sort of early computers, because I can actually show you a piece of software that would have run on the EDSAC. It looks like this. This is the Hello World program for the EDSAC. So it prints out the message Hello World. And when I say print, I really mean print. It would like output it on a piece of paper with little typewriter arms. So, this, unless you know how to read EDSAC machine code, this isn't going to mean very much to us, I don't think. But we can sort of see down here that there's some data that if we focus on that, we can see it has the words Hello World, and that's being printed out there. So it was hard work in those days writing software in this way. You had to think really quite carefully. I can give you a sort of modern equivalent of this, somewhat modern, by dropping into this this little hypervisor here. This is running MS-DOS, which was an operating system that, well, from a long time ago, that then sort of led into Windows. And I'm running this cool program called Debug, which allows me to type machine code, well, actually assembly language, which is a sort of a version of machine code where it's got words instead of just numbers. So it's a little bit easier for a person to write. And it allows me to write assembly straight into the memory of my computer. So I'm going to write the following. This is setting up some information. DX is a register. That's like a holding place inside of my processor. I'm saying set that to the value 0108. That's going to be a memory location. Set some other value into this register AH, that's 9. And then call this interrupt, and then ret, close the program. And I'm going to hit go, and ooh, I did it completely wrong. That's great. Even the simplest program I got wrong straight away. So let me try that again. Oh yes, because I actually forgot to put in some data. So it just read garbage memory. That's perfect. That's good. Right. So put in my hello world, and I'm going to run it. And now we've got hello world. So I'm really interacting really directly with my processor there, in much the way that you had to work with it with the early computers. You were really giving them direct instructions in the language of the processor without any other kind of operating system or machinery around it. Now, in the sort of 1940s and 1960s, all that period, all the software was essentially developed in this way, sort of directly instructing the computer, which sounds like pretty difficult, but because humans are amazing, incredible people like this, Margaret Hamilton, she led the team that wrote the software for the Apollo mission. And so amazing people like this wrote software to make machines like this work, to take people like this to this place and back to this place safely, all just writing machine code like that. And what's really cool is that you can go and look at all of this code online. All of that code that Margaret Hamilton wrote and her team wrote is now available to us. You can see the machine code that was used for the Apollo 11 lander. If you've got, if you're feeling especially nerdy perhaps, or you've got a spare evening, you can go and listen to the Apollo landing audio as the astronauts are going down in their lander towards the moon. You listen to them talking to Houston, mission control, and you hear them saying, "Oh, there's this error that the computer's saying. What is it? Is it bad?" So there's something that 1202 program alarm that comes up. And the cool thing is, you can then go and look in the code, find out where that's from, and then read the reports later about what was going on. You can sort of trace back in the code what was happening back in the 1960s. It was not actually a problem with the code. It was some unexpected interaction between bits of the hardware and the software on the lander. But as we all know, they made it, and they made it to the moon and back. I'm going to sort of make this program a little more interesting, the Hello World program. I'm going to use this as kind of a running example. I'm going to come back to it later in a different language. But I'm going to write, let's say I want to do the Hello World thing, but instead of just writing out the string Hello World, I want to print one letter at a time on its own line. So taking the data and then print a letter at a time like this. So I'm going to write that.
We had a question in the chat.
Oh, great. Yes. I don't know how I can see that. Sorry.
Do you want me to just read it to you?
Yeah, please.
It says, is this going to the vCPU or to the physical CPU? I'm not sure what this was.
In the DOS box, I imagine it's
probably the virtual one, I imagine.
Probably the virtual one. If I was running DOS actually on my machine, then it would be going to the actual CPU.
Right, yeah.
But this is kind of emulated, so I think it's probably not going directly straight through. But what I'm writing here are the actual instructions of the Intel x86 architecture, which is what my computer that I'm running this on, that's what it understands. So it could go directly and it would understand it fine. So this is x86 machine code. Now I know that the undergraduates at Augusta have an assembly programming module, so some of you will be kind of familiar with this stuff. I'm not sure whether you use RISC or you probably use RISC 68K, which is similar but a little bit different. But this is x86, so that can run it directly on here. Any other questions? All righty. I'm going to write my program then to print one letter at a time. So I'm not going to explain every aspect of it as I write this. The idea is that I'm going to store some stuff at address memory 0123. I'm going to move it into this register here. I'm going to look at it and see if it's character 24, which is the $sign. If it is, then I'm going to jump to the end. Otherwise, I'm going to save my memory address, move my memory around, copy my value over there. It's going to be like a little data buffer for me to print out this symbol with a character return on it. And now I'm going to point the DOS system at the right place to print out the character. When I've done that, I'm going to increment my address to move on to the next one. And then I can jump back to the start. And now I've got my little place where I can, this is the new line character sort of area. And then I'm going to store my stuff there, and ta-da, it worked. I printed every single character on a new line. Now, in case you think I'm some sort of assembly programming wizard, I am not. It took me like over half an hour to figure out how to write that program the other day, and I got it wrong tons of times. Because writing assembly it's tricky, and I'd have to sort of train for a while, I think, and practice for a long time to be able to write programs like that sort of instantly. So, of course, this is not how we program these days. We write using higher level, what we call higher level programming languages. And by higher level, there's the code there for the slide for you to look at later if you want. In higher level languages, we have layers of abstraction. These are abstractions, in this sense, I mean hiding details, so that I don't have to directly manipulate the registers in my processor or directly manipulate the memory. I have other language constructs that will hide things for me and help me manage the complexity of the hardware and the software. So, over time, as languages have developed, we've sort of followed an abstraction kind of continuum. There's machine language, machine code, where you're just putting in raw numbers to the CPU. Then there's assembly language, which is very similar. It's just adding some names to things. And then in high-level languages, well, I just use a function called print, and I write print hello Augusta, and that would be fine. So the print command has to be implemented somewhere, and then eventually it will get compiled down maybe to some other language, and down and down and down until it becomes the machine code. So part of this, part of the history of our field as computer science has been about building languages that let us express ourselves and solve more complex problems more easily. And I like to kind of summarize the goals of programming language design then via something which I call the 4 R's. This is a bit of a pun based on the 3 R's of education, which was a Victorian thing: reading, writing, and arithmetic. Well, the 4 R's of programming language design, I think, are roughly that languages help us to read programs, because humans use programs to communicate, so they want to be able to read them. It helps us to write programs, reason about our programs, that's understand how they work and understand when they're going wrong, what's going wrong and why, and to help us implement things that we actually want to implement and not something else. And then also to run our programs more efficiently. So a lot of the sort of effort over the last 5, 6, 7 decades with programming languages is, I think, roughly just trying to maximize these different aspects. And they're kind of competing. So there are some languages that are really about running programs more efficiently. But often that can make it very difficult to reason about the correctness of a piece of software, whether it actually does what you think it does. And reasoning about programs is very important, because we have programs running all over the place, right? It's not just bits of software making the Apollo 11 lander work. It's, software is absolutely everywhere, running our entire societies, our transport, our infrastructure, financial systems, and just everything I do with these things. So there's sort of certainly no perfect language, but I think a lot of what languages are trying to do is maximize these different aspects. And today, I'm going to focus on the idea of reasoning about programs, so being able to control what they're doing a bit more, understand how they work, but also writing programs as well. I'm going to touch on that, but actually I'm going to have the computer write the programs for me some of the time. So that's called program synthesis. So I'm going to be doing this through the technique of types. Lots of languages have the idea of a type system, which is a way of, broadly speaking, a way of sort of classifying the data in a program, and then having a way of checking that the operations that you have, whether you're passing the right things into them and getting the right things out. So, for example, if I have the short little program fragment 1 divided by the string hello, I might assign the classification int to the integer, string to hello. And then my type system is an algorithm that's usually part of my compiler, which goes and looks at this and says, is this sensible? And in this case, it might not be, because the type system might then tell us something along the lines of, well, I don't know how to divide an integer by a string. Maybe you made a mistake. And this kind of type system is really prevalent. Languages like Java and C and C# and C++ have something like this. But what we're all about in this research project is trying to make types more expressive. So the kind of traditional type systems describe what is being used by a program, like what the data is, what it is going in and out. But what I'm going to be talking about today is more types that describe how a program works. What does it actually do inside? And this is sometimes called a behavioral type. It's like capturing the behavior of a program and sort of exposing that in a way that we can then specify it and then have the compiler check for us automatically whether we actually conform to our specification and whether we do what we think we're doing. So all of this is going to be via a technique called graded modal types, or sort of technical artifact called graded modal types. And this is part of a project which we call the Granule Project, which I work on with Harley. So it's a project that's between Kent and Augusta, and we've been going on this project for a couple of years. And one of the aspects of it is this programming language called Granule, which I'm going to be showing you today. So I'm not going to be live coding more assembly code. I'm going to be live coding Granule code instead. So one kind of aspect that we've been looking at in Granule is understanding how programs use data, not just what the data is, but how it's used. And actually, this is something that's been thought about in computer science for about 30 years, really. This idea of treating data as actually a resource, that's something that has some constraints on it or can get used up, something that we want to be kind of a bit careful about how we use it. Now, we can certainly understand the idea of being careful with some data now, like all pictures of my family on my phone. I just want them to be available to me and my friends and my family and other people, or the password that's on my phone, or the GPS position, and so on. So we're used to thinking now of lots of data having some sort of resource constraints on it and some kind of constraints on what's done with it and where it goes. But we can kind of apply that idea to every part of data in a computer, actually use that to help us describe and specify program behavior. And that's what we're going to do today, using this idea that's been around for more than 30 years now, the notion of something called a linear type. Now, in normal programming, when I have a value like, when I say normal, I mean most programming languages, when I have a value like an integer or a character or something, I can do whatever I want with it. I can move it around. And in the assembly code program we just did, I had this string, and I moved one of the characters a bit at a time into a certain place of memory, and I printed them. But one of the things that linear logic kind of captures for us in a type system is that some data should be treated like a resource, and therefore it must be used, but it must only be used once, and exactly once. So you can't use it more than once in your program. And once you have used it, it's gone. And if you've got it, you can't just throw it away, you actually have to use it. And this is an idea that's been around for a while, and that people have used this as the basis of lots of other kind of reasoning principles and reasoning tools. And that's what we do here. So I'm going to switch to my code editor here, the Visual Studio Code. This is Granule code here. I'm going to write here, and then I'm going to switch between the code, and this is the interactive mode for the Granule compiler. So here's the sort of the simplest functional program you could ever write, really. It's called the identity function, takes in some input, which we'll call x, and returns it straight away. So this up here is the type signature. It describes the input and output values for this function. So it says and it works for all types. So I can use this for integers, I can use it for characters, I can use it for lists of characters, and so on. And this is a linear function. It takes in something and it uses it by returning it. And so I might start trying to write some other really basic functional programs that you would learn in sort of Functional Programming 101, which many of you may have seen something like this. So what I'm doing here is I'm taking a data structure, which is a pair, and I'm saying that the pair contains things of type A and of type B, so it contains two things. And I want to throw away the second part of the pair and return just the first part. It's called projection. So this is pattern matching on the pair, breaking it apart, getting the first value and returning it. I'm going to write another function. Which one should I write? I'm going to write dup, which takes a value of type A and returns a pair of A's. So its implementation looks just like its type. Now I'm going to reload this in the Granule interactive mode, and I get two errors. Linear variable y is never used up here, and down here, linear variable x is used more than once. So we violated the principles of linearity. Over here, we threw something away, and over here, we tried to use it twice. Now, this seems very restrictive. These are some of the simplest functional programs I can think of writing, and we can't write them. But of course, there is a way to write them, and I'll get to that in a moment. But first, I'd just like to, I'd like to show something that linearity is really useful for on its own, which is a sort of famous example in this space, which is the use of linear types for capturing protocols of interaction, stateful interaction with your operating system. And a classic one is operating with files. So I'm going to write a short program which does some sort of I/O behavior. What it's going to do is it's going to open a file I'm using a command that's part of the built-in library for Granule. I'm going to open a file in read mode. I'm going to open the license file, and that's going to give me back a handle to the file. It's like in many languages. I'm going to read a character from my handle. And what this does is it gives me back another handle and a character. So this operation, from the point of view of the type system, this read character takes in a handle and it uses it and it destroys it. But it gives me back another handle, which then I can then go on to use to interact with the file. So I'm going to let's see, I'm going to close the file. Like this. And then I'm going to return the character. So let's make this be a function that returns a character. And my parse error is because I need to do that. So then if I execute one char, I get the letter C because the license file starts with the word copyright. Now, a thing that can happen when I'm programming with files is I might actually forget to close the file. My type system here won't let me do that because it says, hey, this handle here, h1, it's a linear variable and you didn't use it. And the only way I can use it is via my close handle function. That's the only way I can sort of get rid of it. It's a sort of built-in that lets me actually say I'm finished. And if I didn't do my close handle, then that file would be sort of locked forever and my operating system wouldn't know that it needs to sort of give other people access to it. So I can put that in here. So that's something that's useful. It's sort of making sure that I follow that protocol. Another thing is that once I've closed it, I shouldn't be able to read it again. So let me try and read another character.
Hey, Dom, we have a few questions in the chat.
Right.
Arca asks, what does the empty brackets mean? The open and close parentheses, I think.
The empty brackets.
The open and close parentheses where you, for a close handle there, right?
Oh yeah, cool. Yeah, sorry, thank you. Yeah, great question. That is called the unit type. It looks like this. It's like a type that contains just one value. You can think of it. If you think of pairs as something that has two values in it, this is like a pair with no values in it, and so it's just like an empty box. It's useful in sort of functional programming when you want to you have a function that sort of returns, but it doesn't return you anything interesting. It's a bit like the void type in Java. Does that answer your question? I should pop up I should work out how to make the question.
Yeah, there should just be like a chat window.
Tell you what, I'm going to open that on my other computer, so then I can see the chat on my other screen.
Yeah, that's fine.
Great. I can't see the previous messages, but I should be able to see them going forwards then.
Yeah, there's one other new one by Stefan, and then you'll be able to see the ones coming after that. So Stefan asks, what happens if the file does not exist or file is empty, i.e. if there's an exception?
Great question, yeah. So an exception will happen. And actually, this type up here, this is a bit like, if you've done the Haskell programming, this is a bit like a monad that we're using here. It's a bit like the IO monad. But this is actually really hiding something. And this is starting to get into the sort of gradation idea. So this is actually hiding, you can put some more information here, not just that it's IO, but you can describe exactly the kinds of side effects that are going on over here. So I think exactly what is happening here is opens, reads, closes, and IO exception. So this is telling our system that this can throw an exception. And so if I want to use this in a safe way, I actually need to wrap it in a try catch block, which will then allow us to sort of delete the fact that the exception can happen. So at the moment, if an exception happens, well, we haven't wrapped it in a handle, in a sort of try-catch handle block, so it will cause an exception. It's kind of part of the language we're still working on. So hopefully that answers the question. So actually, let me run this now. Past error somewhere. So I can't run it because this H2 is never used. Okay, so I try and close this handle. But now I see that H1 is used more than once. So I close the handle here with H1, but then I try to use it again. So if I was in another language, like, well, basically every other language, I run this code and I get a seg fault because which is like a hard exception. I closed the handle and then I read from it again after it was closed. So with linear types, it's nice for encoding this kind of linear chain of events that I have to do from an open to a close. I always have to close, and once I've closed, I can't do anything else. So that's a sort of classic use case, sort of well known in literature, and this just shows the sort of Granule way of doing it. Okay, so let's go back to these programs. Now, of course, it was anticipated by people working on linear logic and linear types in the 80s that sometimes you do want to have a value that is used in a non-linear way, like you need to throw it away or you need to copy it. So they introduced an idea from logic called a modal operator. And modal logic is this sort of really amazing area of logic where it's basically trying to extend logic to capture reasoning about sort of things that are outside of the logic and capture wider or interesting properties, things about provability and knowledge and where things are true in which worlds and so on. And so, so I'll answer that question in a second. I've just seen pop up. We can use this modality here in Granule. It's written for us as this sort of postfix thing. If you've done any modal logic, it's a bit like the box modality. We're saying sort of a box over B. And I'm going to use it over here as well. And then in the pattern match, I'm going to do this. So you can think of this as being like a box.b, which gives us the capability to use this thing inside in a non-linear way. So by doing this pattern match here, I'm like smashing open the box, and now I can use y non-linearly. In this case, throwing it away, and in this case, duplicating it. And that's fine. So that's our sort of escape hatch from linearity to non-linearity using this modality. And what's really interesting is that the sort of standard rules of modal logic, they can be used and sort of applied inside this type system to track which things are nonlinear and how computations depend on nonlinear things. So the things that they depend on have to be nonlinear and so on, and sort of track back. We're going to see that idea a bit more in a moment. So a really great question from Arka, going back just a second while I'm still here, is we also didn't use the empty brackets that's called the unit type. Well, actually, we did use it by doing this pattern match. This is a kind of concrete piece of data, and by matching on it and inspecting it, that counts as a usage. So these variables here, we've got some value bound to it, but we haven't used it yet. It's sort of something that's still inside the variable that hasn't been used, hasn't been evaluated. But in order to, if I put a variable here, then you're absolutely right. This would give me an error. It'd say, hey, linear variable x is never used. But what I'm doing by replacing this with the empty brackets is I'm taking that value, I'm inspecting it, saying it must be equal to the unit value, so it consumes it. And because the unit type only contains one thing, I know that this pattern match will always succeed, so I can do that. That was a great question. Thank you. Right. So I'm down here and I've got my modalities. Now, as I said at the beginning, there's this kind of binary view of things, but what we're interested in is a gradation of things, a sort of a spectrum of things. So this modality gives us like a very binary view of the world. It's like linear or nonlinear. There's linear stuff or nonlinear stuff. But what we're doing here is, with graded modalities, is that we can place some extra information which tells us exactly how nonlinear something is. So in this case, this would be 0 because we're throwing it away, and here it's 2. So it's like a quantity that tells us how much something is, how much you're allowed to use it. So that's fine. And if I put 1 here instead, then I get an error saying, well, it's telling me in terms of a theorem, it's saying the following theorem is falsifiable, 0 equals 1. Like 0 is not equal to 1. We used to have slightly better error messages, but I've been doing some work on this and I think they've gone away. But basically saying, hey, you actually do use this thing. You're saying, sorry, if I put 1 here, you know, our signature is saying you can use this once, you have to use this once, but the actual implementation is not using it at all. So we go like that. So in the language, everything's very explicit. You have to sort of put the boxing and unboxing in yourself. So Stefan asked, does A box cast to A? Not implicitly, but we could do something which I'll call extract, which says A box goes to A like that. So that's fine. But I can't go back the other way for reasons I can explain once I've explained a little bit more stuff. So Richard asks a really good question, which I'd like to come back to at the end, if that's okay. I will come back to that question. Thanks, Richard. Okay, so let's just pop back to the slides for a minute. So the modal type analysis is this binary view. Graded modal type analysis is about this spectrum. So let's go back to our program from before, our assembly program to print something 1 line at a time. I'm going to do the Granule version of that program now. Now, because we have a type system and Granule forces you to put a type signature at the start of, you have to write a type signature. So it's kind of forcing the programmer to think about, well, what does this function do? At least what's its input and output, and how is it going to use that data? So I'm going to I know that I want to take in a string, and I know I'm going to do some kind of side effects. So it's going to be one of these diamondy things. but I know exactly what kind of side effects I wanted to have. I wanted to have the side effects of some standard outputs. That's like printing information out on the terminal, on the console. So this string is linear. So what I'm saying here, the default sort of subsystem here is linear. So I'm saying, well, I have to consume it in its entirety. So I'm going to use a, oh, actually, I was going to do another example first, because I need to use something called the maybe data type. So if you'll forgive the digression for a second, we'll come back to this program in just a moment. I'm going to comment that out. And just show you the maybe data type here, which I'm going to use in a moment. I'm going to use this function. I was about to use this thing called string on commas, which takes a string and gives me a maybe of a pair of a character and a string. So what maybe does, it's a useful common data structure in functional programming, sometimes called an optional type. It exists in lots of languages as well, like Java. It says that a maybe for A's, it's either nothing. You can construct these values as nothing. That's the word we use to construct it. Or it's some A. So this is like a package where it's either there's nothing there or there is some of these things, there's one of these things. So a kind of standard function that you might have in a functional language is this from maybe, which says, well, let's say you want to sort of, you're thinking, oh, can I take a maybe A and can I get an A out of it? Can I always do this? Well, that's going to be problematic, because what do you do in the none case? You don't have anything of type A to return. So there's this function called from maybe, which is quite well known as a Haskell world, where first you take a value which is like your default, which you want to use when this thing is actually none. And so that we can always get this A. So I might start trying to write that here. And actually, one thing I sort of mentioned earlier was about program synthesis. So having your language tool write the program for you. And I can do like a very tiny amount of that right now with this program, where what it's done now is look at the maybe type and say, well, what's all the possible cases you have to consider? I pressed a little key combination in my editor and it rewrote that for me. So it says, okay, well, you need to do something here. And I've just asked it to fill that in for me. It says, okay, well, you can return this value X. Now down here, I'm going to be in trouble. I've asked it to synthesize the program for me, but it's kept it as a question mark. Because if I return X, then we're going to have a linearity problem because we didn't use this thing here, which was called M0. We'll rename that to Y. But if I use Y, well, then we've got a problem because we didn't use this X, another sort of linearity problem. So in fact, what we need to do is say that this default value gets used 0 or 1 times. And I can represent that using the graded modality again. It's technically a different graded modality to the one we saw earlier. This one was a graded modality where its grade is a natural number, and that's for capturing exact usage. But this is a graded modality indexed by an interval of natural numbers, capturing the range of uses. So it's useful when you want to do different things in different branches. And what's cool now is that I can get this program to be completely written for me automatically by the computer. And we see in the sum case, then we return the sum here. Because this was a linear thing and we really had to use it inside of here. And in this case, it's the 0 use. So check the questions. Okay, so there's some sort of more general questions which I think I'll leave for the moment. Any specific questions about this kind of example right now? So Arca says, is non-similar to unit in the sense we don't need to use it, but then we can return none. Yeah, so this is, again, like a concrete value. We've matched on it, so we have used it. We sort of looked at it and we've inspected it, and that counts as its use. So it is exactly like unit in that regard, yeah. Good question. Okay, so I'm going to use my string on cons function, which is part of the standard library. I'm going to use that down here, and I'm going to case on the result of this. So it could be none, in which case I'm done. So I'm going to do this, which is a sort of don't do any side effects, just return the unit value. Or I could have a character and a string, in which case I want to print out that character. I'm going to make a little helper function in a second. What's the name of the thing? So I want to do to standard out, and I'm going to make a function up here, which I'm going to call character NL, which takes a character and turns it into a string by adding it onto this string here. This is going to then add the new line character on. So I'm going to output that standard out, and then I'm going to recurse. So this should be fine. Okay, so let's try it out. So I got what I wanted, and then this is just the return result here. So what's nice about this compared to, say, like writing in assembly, okay, it's a bit easier to understand, but also by writing the type specification, it's kind of really constrained the sort of programs I can write. I've got a string, I know I'm going to have to look at it all. I can't sort of miss part of it out and sort of not do something with it. I've got to sort of deal with it all in some way. And I know that I need to output stuff to the screen. And I can't do anything else like read things in or open files or anything like that. No, the only side effect that I'm allowed to do, as given by this description, is do an output side effect. But, you know, I could
we have a question from YouTube for you.
Oh, cool.
Grace Fu asks, is there a difference between the citation one, so maybe talking about linearity, and not having any box at all?
There's, for the exact usage, they're the same. So I can put this up here, and I can have there's a sort of built-in thing. I think it's going to let me do this. I think it's called use. Right. So this is saying that linearity is sort of isomorphic to the idea of a box one. So Grace, you're absolutely right to ask that. You're right. There is no sort of distinction there, but we can change the meaning of one, and there's a sort of sensible way of doing that, and then this stops making sense. So we'll see what I mean by changing the meaning of one perhaps a little bit later. But these graded modalities basically have their elements drawn from a semi-ring, so some algebraic structure, and so we have an element that we call one in that semi-ring, and it doesn't necessarily have to have this property. So this doesn't necessarily hold for all the kinds of graded modalities that we could have, but it does here. Thanks. All right. Okay, so we did this program. One thing that we might find tricky about this is that it doesn't, there's things we could do that maybe are not what we intended. Like we could, I don't know, we could say some other things here, boo, or down here, we could actually not do the recursion, and we could just output the entire string here as well. Let's do that instead of that one. So that type checks, but it doesn't do the thing that maybe we intended. So we've kind of gone some of the way in terms of sort of specifying the behavior of our program with the type, but not a long way, just some of the way. So what we might do is start sort of breaking this down and trying to build the sort of primitives of this that sort of force us to do the thing that we intend. So, okay, this is like a small, simple example that we can easily test. But once you get into sort of bigger pieces of software that are very complex, then sort of one strategy is for you to break them down and sort of specify each of the components a little bit more carefully. So I'm going to sort of, as the last then sort of example really, show you a few of the other features here, which show other parts of the type system and use it for this example. So I'm going to define here another kind of data type. It's called a vector. There's a bit of extra syntax here, so if it's a little bit kind of too much, then don't worry so much. But it's basically a data type of lists that includes in the type its length. So the list can be empty, which we write as a nil, and well, it's a vector, sorry, and that has size 0, so it's the empty vector. Or we can do a cons, which is like when we add something onto a vector, and you do that by having an A, having a vector of length n, and then you get a vector of length n plus 1 out of it. So we could use this to describe the data structure holding our characters that we want to print out, so a vector of characters. And we could write a function, let's call it character per line. Well, let me just call it loop for the moment. I'll think of a smarter name for it in a moment. And what it's going to do is take a vector of characters, and then we want to sort of make sure that we process each character in turn. So I'm going to do that by, instead of sort of doing it directly, I'm going to take a function which takes a character as input and then does some side effects like that. And then I'm going to get an output. So let me try and write this function. Try and keep an eye on the zoom. Right, so I've got the x's and the f. Let me just get a little bit of help, at least, in doing that function, maybe. Oh, I've got typos. Okay, so it went this far, but we can kind of see fairly quickly that we have a linearity issue. So in this case, where I've got to the end of the vector, I have this function f, but I'm not using it. So we might switch to the modal version here and say, okay, well, I have to use this thing non-linearly. And then turn that into the f, sorry, unbox it there. And over here, okay, I'm going to, what am I going to do? I'm going to apply f to x. That's going to produce some side effect. Then pattern match on that result value there, and then do the loop on the rest. Oh yeah, sorry, I was noodling around with that and I forgot to revert it. And down here, the mistake is that I need to just return that value. Okay, now something that's interesting about this type is we've said this is non-linear, this function here. We can actually be way more precise than that, because we can use this bit of information, the length of the vector, and we can put that in our box here. So we've specified that we're going to apply this function exactly n times, where n is the size of our vector. So that's what we're doing here. So we've got this function that we know is which is going to process every single character of the vector by applying this function. And it's not going to throw any of those away or just yeah, sort of pattern match on those characters or something. It's going to apply this thing. It's got to apply this function n times. So it's sort of heading towards verifying it a little bit more. There are some other things we could do which would have this type, which would be not what we wanted. But we're still working on some features that would let us to constrain things even more. So how do I finish this thing off then? So I'm going to, I'm actually just going to replace this with an import library for a second, vecsimple, which has the same stuff. I'm going to define my function I wanted a long string like this. And what I'm going to do is I'm going to use a function that's coming from this library here called string to vec x, which gives me a way of turning a string into a vector, and then I can run my loop on it with the function that applies char NL, and then to standard out on it like this. Okay, so now I can get my program that I wanted. So it's just sort of pulled it apart and specified it in a slightly more fine-grained way. Now, I'm going to answer that other question in a moment. Let me jump back to this presentation here. So what's going on with graded modalities kind of informally is that if you know about modal logic and you're familiar with the box and the diamond, these are sort of the standard modalities. Graded modalities sort of like explodes this out into this indexed family of modalities, but where this family has some sort of structure associated with it, sort of distributed around it. And the way that we use them, or the useful kinds of graded modalities, are the ones where this structure sort of matches the shape of our proofs or our programs, or the semantics of our programs. So we can use this to sort of reflect properties of the program back up into the type system. And that's what we've been doing here. We've been using graded modalities to sort of capture how values are used, how many times they're used, and also capture side effects as well. So the diamond kind of syntax, that was these kind of graded possibility modalities or graded monads, if you know about that kind of thing. And over here is the graded necessity. So this side is kind of more about like capturing data use, and this one is more about capturing sort of side effect properties or sort of forward data flow properties of the program. Now, in the case of the box, what's going on is that these grades, they come from a semi-ring. So it's an algebraic structure which has something that's like multiplication, something like plus, a 1 and a 0, and then also, it has an ordering on it as well. And then if we were looking at this from as a sort of Hilbert-style axiomatization of the logic, then we get these operations which tell us basically the things we can do with our modal operator. And now they're actually controlled by these operations. So we get an operation that's it's often called the for axiom. So if you squint and don't look at the grades, the indices, then usually it says box A goes to box A. It's sort of expanding it. But now we can only do that at the grade R times S, and it expands it into box R and box S. So if we think of this as like the number of usages of something, like 10 uses, then we can split that into 2 lots of uses or 5 lots of uses, for example. And this is used when we're composing programs together. If we have 1 use of A, then we have an A. If we have 0 uses of A, then we can just get the unit type. I've called this 1, but that's a slightly unhelpful overloading of notation. This would be unit type. And so on, these other things like box R plus SA goes to box RA and box SA. So this is like saying if I've got 10 copies, I can split it into 5 copies and 5 copies or something like this. So the type system is sort of built from these constructions, are sort of embedded into the way that you build programs. And there's lots of work about how you model this and how you build type systems on this. So to kind of summarize what's going on, and then I'll deal with these great questions that have been adding up, these sort of general questions. So what Granule is doing is it's like combining a few different kind of type ideas together. We've got linear types as the basis. That's treat data like a resource. We have these graded modalities that let us kind of have some fine-grained reasoning, quantitative reasoning. And then we have this idea of what's called an index type. That's things like vectors with their size. And that lets us be a bit more precise and sort of connect together the dependencies in our program. And all this goes together to give us some fine-grained program reasoning. And we also use it for program synthesis as well, which we've seen a bit today, where I press a key and the computer writes the program for me. So the take-home messages are that grader types are about giving you precision about how your program works. That precision leads to better reasoning, more verification, and you can get programs written for you. Now, one of the things we're exploring at the moment is then like using that information to help the compiler compile your program into something that's more efficient. So that's the other R of the 4 Rs, making programs run faster. So we're doing research in that space. And there's lots of other things in Granule I haven't been able to show you. We can track things like the privacy of data. That's one of the other graded modalities that's in there. We can track sort of computational cost, how much things how much execution is, or execution units are used by your program, things like asymptotic analysis, sensitivity to values, like how much does the output change based on input changes, and so on. So those are sort of lots of other things that are in there. And if you go and look at our project website, there's lots more videos and talks and papers there. And I just wanted to thank my collaborators, my students and colleagues at Augusta. The students are in blue and green here. The green are the people who've recently joined the project. So thank you very much. And yeah, thanks for inviting me.
Thanks a lot, Dom. Great talk. I really enjoyed it. There's a few extra questions on the chat.
Yeah.
Time to answer those or not?
Yeah, I will answer them all. So Richard Eisenberg earlier said, what if readcar throws an exception, then we would never close the file handle, or if close handle throws an exception, we would never use C. Is that a problem? Absolutely, yeah. So if going back to this, let's say that read char throws an exception before really dealing with the handle, or close handle throws an exception, and then we never actually use that C. It would violate linearity. And this is actually, this is definitely a problem, and it's something we're sort of actively researching at the moment. We have a way of sort of doing something a little bit more interesting here with a try-catch block, and then looking at the sort of interaction between linearity and exceptions. But it is something that people have thought about a bit, like there's a kind of conflict between exceptions and linearity. Like exceptions mean that sort of it can violate linearity. At the moment, basically the sort of get out for us is that the runtime system will kind of collect up those resources and free them for you. But actually we are working on sort of more like fine grain, like something internal to the language to kind of let us understand and that situation a bit more. We do have a try-catch, but we're still a bit of a work in progress on that one. Eric asks, does Granule exploit the modality on types for erasing irrelevant data, i.e. as in QTT/IDRIS? Right, so things like this, where you said 0, so you know that it can be erased. At the moment, no, but there's no reason it couldn't. We've done some other work that's to do with erasure. But yeah, that would definitely be a place where it would be a sort of an obvious optimization to know, like, oh, we don't need it there. We have a sort of work in progress LLVM compiler, and we're sort of hoping to explore those things in the future. But at the moment, it's sort of interpreted, and it doesn't really use the grades in interpretation. But that goes back to the sort of work in progress thing of, where was it? Of using this precision to make programs run faster. You absolutely can and will hopefully do that soon. Ruben wanted to know whether there's some degree of type inference. So the type checking algorithm is a bidirectional algorithm, so it does have a sort of inference part to it, and that is what you're seeing. There is a bit of that going on to let me do the lambda here, but it's fairly heavy on having to. You have to put the type signatures at the top, and those are going to get pushed into your program. Without those, we'd kind of be a bit scuppered. We've thought about kind of exposing a bit more inference. I mean, you can actually I guess, already do that in a way. So you could say, what is the type of lambda x goes to x plus 1? And it looks like there might be a bug there because it's saying that it's exposing a unification variable there, which it's forgotten to rewrite. So this is hooking into the synth part of the bidirectional algorithm, the sort of inference part, but I think it's not applying the substitution there. So we're sort of, I know we're not super into the idea of having full type inference. I think part of the philosophy here is like forcing the programmer to think about what they're doing via the types. Oh, I feel like there was another thing I mentioned. Oh, Eric says, why pick linearity as the default instead of unrestricted? Because if you pick unrestricted as a default, you can't give the same level of guarantees. It's sort of much easier to start from the restricted base, the very restricted core, and then use the graded modalities to sort of weaken it back up in a sense, to sort of add the structural rules back in a controlled way. We're working on a version of Granule now that's more like implicitly graded, so the grading is happening everywhere, a bit like in linear Haskell, but also having the graded modalities as well. So, so the linear arrows would, you could have more like Cartesian arrows. Actually, one of the things I was going to mention and forgot about is the fact that the box is actually an alias for 0 to infinity. If I see this, this is actually an alias for 0 on the extended natural numbers to infinity. So that's another one of these semi-rings that lets us, it represents arbitrary usage. I think we found that actually there is quite a bit of linear stuff around, and it's been interesting to kind of take linearity as the basis and see what happens. But yeah, we can explore different kind of place lines.
Hey, Dom, we have maybe I can squeeze a question from YouTube in for you.
Yep.
I'm not sure how to pronounce their name, but maybe it's Jin Cohen, maybe. Sorry if I'm mispronouncing their name. Any plans to extend Granule to reason about concurrent programs?
Oh yes, well, we already have that in place actually. So if you want to go and download and play with it, you can, and we have this session types sort of set up, which builds on the idea of linear types. So there's this idea in programming language literature called session types, which is based on linear types, essentially, where you have channels and you use the types to describe what you're allowed to do with that channel. So this is an example here which says, oh, I have a channel and I can send a Boolean on it and I receive an integer on it. And it uses the linear typing idea in basically exactly the same way as the file handle example to make sure that we exactly follow that protocol. So I send here on the channel a bool, I receive something n here, and then I close my channel, that's end, and I return that. I'm in a branch of Granule where I haven't tested this. So I am, good type check, I was thinking for a little bit there. So if I did something here, like I violated the protocol given by the type, and I sent another Boolean here, then I get a type error. And hopefully the type error will be moderately understandable. So it was saying I expected a receive int on this line, but I got something that was a send. So we see there's like a mismatch in the protocol. And then, so you can describe interactions on channels, and then you can fork a thread, which gets one side of the channel. This is linear fork. So this is, you give it a function which takes a channel that has S protocol on it, returns unit, and then what it gives you back is the dual, which is sends become received and receives become sends, from which you can use to then interact with it on the other side. It's like the other end of the channel. So that's what's going on in this example here. Put that back. So then I can run the example once it type checks. And so what that's done is really started a process that run in parallel, and we sent an integer, sent a bool across and an integer back the other way. So there's stuff about concurrency there, which you can have a look at. Great question, thank you. I'll go back to, I don't see any more questions on the YouTube, so I will jump back to the Zoom questions. How can we define custom modalities in Granule? Good question. This is something we really, really want to do, but we can't do yet. So at the moment, if you want your own modalities, you have to go and add them into the compiler. It's not terribly hard, but what would be great is to be able to have them as a library. So the ambition is that you can have a library which comes with perhaps its own reasoning principles, or you think, oh, well, actually what I want to do is track this property in my type system. So you would be able to define your own semi-ring internally and then have that lifted up. That comes with quite a few technical challenges. So at the moment, we compile, we generate theorems that come from our type checking that then go down into an SMT solver. So you can write some like fairly complex constraints sometimes, and they go to the SMT solver to be as part of the type checker. That's why sometimes it's a bit slow. So I can write kind of some interesting things, like I can have a vector of A's where I can use each thing twice, and I can turn that into a vector of size 2n. So I can write kind of complex things in the types, dub list, so nil goes for nil, and oh no, that's the oh, that was not too bad type check. But you can kind of express quite a few things there, and it goes to the SMT solver. Sometimes you can make things too complicated, and the SMT solver times out. So if you've got user-defined stuff, the tricky thing would be, you know, how do you then solve equalities over that user-defined stuff? And do you make the user define a decision procedure and so on? So one of the piece of work that Harley and I and my student Ben have been working on, we have another language called Gertie, which is a fully dependently typed language with grading as well. And there we think that's a nice setting for doing this, because you can use the dependent types setting to let you sort of internally check the properties of the semi-ring and say, well, these properties hold for this algebraic structure, therefore I can use it within the type checking algorithm. But yeah, that's more things we're interested in doing. So Arca asked, can you please explain the star and the plus on modalities once more? Absolutely. So let me give you a different example about cake. I'm going to import my cake library. Every linear type language should have a cake library. And it gives me a function called have, which goes from cake to cake, and it has another function called eat, which goes cake to happy. So let's say I have, what I want is to have my cake and eat it. So I want to take a cake, have that cake, and eat the cake. And we know that that's going to violate linearity. But if I have a modal cake, let's say I have two cakes, then I can have one and eat the other, and that's fine. So what's going on here is that in these two parts of the program, they're both using a cake. So that's when we use the value cake, it's sort of counted as one in the type system. And in these two parts, they're then getting added together. So the plus of the semi-ring is being used to add up the resource usage in each part. So what I could do is say, hey, at the end, I want to have 4 cakes back, and I want to be 6 times happy. So I'm going to box these up. This is called a promotion. And this is saying that here I need to, I'm going to multiply the resource usage in here by 4. So I use cake once, so I'm going to get 1 times 4. Okay, here I get 1 times 6. and then these get added up because they're in different parts of the program, and this becomes 10. So let me change this and have like a pair of cakes. So I'm going to have a pair of cakes at the end. So now what that's doing is this little subterm in here is using 2 cakes, right, and having 2 cakes. But I'm saying I want to have a pair of these cakes at the end. And I want 4 of those pairs. So when I do this promotion, that's the multiplication again. So it's 2 times 4, that's 8 plus 6. So this thing over here needs to be 14. And if I put anything else, it's going to complain with this amazing error about a theorem that's being generated inside being false. So the multiplication is about how you scale resources, promote resources, and it's useful when you're composing things. And the addition is about adding up the resource usage from different parts of a program. Does that, hopefully that answers the question, Arka. Richard, you have a range grade in your example program. Yes. Does that mean your semi-ring is over ranges? Yes. Or is your semi-ring the naturals and you can specify 2 grades to form a range? In either case, how does it work? I'm not sure. 2 grades to form a range. It's the semi-ring of intervals.
Yeah, but I think his answer is yes, though, Dom, because we do it based on pairs of a high and low, and then that interval that's the elements of a semi-ring, or pairs of high and low, right?
Yeah, it's a pair of high and low. The high one has to be above the low one.
Yeah, and then we do interval multiplication until we're all
yeah. Right. So if I do, so I've got 1 to here. If I did something like I know this is just thinking on my feet here to make a different kind of example, using it to show that then I'm going to do from maybe twice. Kind of. I don't know what I've screwed up here. Oh, yes, I do. I need to rebox these as a terrible error message. Oh, no, I reboxed the wrong things. Sorry, it's these ones that need to be boxed. Right, so then I get 0 to 2 because I've done 0 to 1 and 0 to 1 and added them up. Another option would be to have sets, like a set of usages as well. So that could actually be more interesting here and have like 0 or 2, but not the one in between. And that would also be a semi-ring that you could have. So one of the axioms you included allows subgrading. Yes. Does that mean, e.g., 1 is not less than 2 in your semi-ring? Yeah. So with the exact grading over here, there is an ordering, but the ordering is equality. So I can't do this and I get a type error because I'm trying to make 2 equal to 10. But over here, it's the interval inclusion. So I can put 0 to 10 and that type checks because it allows us to over approximate things. So this lets us do kind of approximation through our signatures.
Yeah, and for
that's
each semi-ring,
same notion of ordering. It's just, well, it's a different ordering.
Yeah, because for each semi-ring, we can define different orderings.
Yeah, so this is using really the natural number ordering underneath. It's not that we're not forcing equality on the nat parts inside of it. So it's a different ordering for the range. Yeah. Hopefully that answers your question, but feel free to come back to me. So Eric asks again, in which sense isn't Granule fully dependent typed? I.e., what's the difference with our language you just mentioned? Well, Granule doesn't have full dependent types because I can't promote arbitrary values into a type. It has index types, so it has GADTs, which you might be familiar with from Haskell. So here I had this like natural number, but it exists at the type level as a type index. But if I had full dependent types, then I could do things like, well, I could make a list data type. Let me call this something else. And maybe I could do the length function on lists. Whoops, list of 8 int. And then I would be able to do, I'm going to have to do that. So I'm going to have to make this discardable because I'm not looking at the elements. So okay so far. I need to unbox here too. And then I would be able to do like the map function, which I could take, let's call it a list like this, and then a function a to b, and then I would be able to do cool things like write length of x's in there to do the map function. So I'd be able to reuse this value at this function at the type level and treat x's as something I can use at the type, and it doesn't let me do that. And something like QTT is more that kind of speed. It will let you do that kind of thing by just treating that as zero use at the type level. Ruben says, can you give an example of using the same semi-ring but with different orderings? I can give you an example in theory, but I don't think we have that in Granule because we need to we identify the semi-rings by their type. And so that comes with its ordering, and you can't sort of reuse that type with a different ordering. But you can certainly imagine having a natural number semi-ring where it has the normal ordering. So you can do things like this and put 3 here. For us, no, we don't have that anymore. You could easily add something like that and say, like, have a version of nat which has an ordering and say, oh, this 3 is the natural numbers with the less than equal ordering or something. Have a different semi-ring that uses the same values underneath.
What would be the use case for that?
For doing that kind of approximation, well, you could just use these instead, and that gives you that already.
Yeah, I think that, another answer might be like for that particular one, yeah, you can do the same thing, but you might have different orderings because of different types of analyses you want to do. So you want to have a different way of relating those analyses would be different. For example, if you're using the semi-rings to like embed different types of substructural logics, you might have one ordering that orders based on having certain structural rules, and another ordering that might do it a slightly different way because you're interested in having a relationship between these two things in different ways. So I think you choose the ordering based on the analysis you want to do.
Yeah. So, I mean, one thing you could do is quantify over the semi-ring as well. So these are all valid programs. I've said for all semi-rings, I can do 0. Just use a sort of kind signature, a little type signature here to say this is the 0 of this semi-ring K. And this works for all semi-rings because they have a 0, and that means like discard here. So duplicate, I can do this if I say 1 plus, well, actually I think I can write 2 here, and I think it desugars that into 1 plus 1, yes. So it knows that you can inject, there's an injection from natural numbers into any semi-ring, right, by repeated addition of 1. So this is saying what's 1 plus 1. And that's fine with my program, so I use it once and once. So there's lots of places where I can sort of abstract on the semi-ring, but I cannot do that here because this is not available for all semi-rings. This uses like a built-in that only works for nat. So it says, I cannot unify unifiers to quantify type variable k of kind co-effect with a concrete type nat. Oh, this is an alias for the word co-effect. So that perhaps relates to Richard's question about having multiple semi-rings present all at the same time. yeah, Granule has multiple semi-rings present all at the same time, and you can mix them together as well. So you can have multiple grades that then get multiplied into a product of grades. That doesn't work on this branch because I've been just re-engineering that, but I can show you that in just a second. So he asked, when I say A2, is that the same as A2 to 2? It depends what you mean by the same. Actually, I'm not going to do that. Let me answer that question in a different way. What have I still got here? Still got this version. Okay. So I could replace this 2 with interval over nat. So in that sense, I can treat 2 as I can treat 2 as interval nat, and that turns it into 1 plus 1, and 1 is the interval 1 to 1 here, so that becomes the interval 2 to 2. Yeah, it depends what you mean by the same. Yeah, so you can. Maybe another question is, can you sort of arbitrarily cast between? Well, not arbitrarily, but can you cast between the two? And so if I had this as really nat, but I made some other thing which I wanted to be 2 to 2, the interval, I think this will be not happy. It is happy. The reason for that being happy is...
I was fully expecting that to the break, but I think it comes down to the fact that nat and intervals have the mapping between them, right?
Yeah, but the other way might not work.
Right, I don't think the other way will work. Not in this, not in Granule currently.
That could be a bug.
It does work. Yeah, that might be a bug.
I mean, I've just been going through a load of stuff to do with how you...
Nat to intervals should work, but I don't think intervals should nat work.
Well, the thing is, I think that it might be treating this 2 as 2 to 2 here.
Maybe. Weird.
But it does have multiple
language
at the same time. So there's sort of examples in our paper where you have like, well, I just think the compilation of this doesn't work right now, but you can take products of grades as well. What is the kind of box? My guess is it's for all S. Yeah, that's right. That is the correct kind for box, yeah. Well, I think, I don't know if I can actually write. No, it won't let me pass that, but yeah, that is the kind of box, yeah. So another one is levels, like where you can have private and you can't write things like this. So that's another semi-ring that's in there. You're not allowed to write that, but that's okay. I think there's a scale function. No. There are some other graded monad ones in there as well. Okay, so another one from Richard. If I have f of type t goes to something, and I call f, are there extrinsic properties you can say about the use of the argument? I've always struggled to understand what it means to use something once without resorting to concrete syntax. Well, when you say t, is that like a concrete non-polymorphic type?
Yes.
That depends on what's in scope. So you can, if its constructors are in scope, then you know that someone at some point is going to consume it by pattern matching on the constructors, essentially. You might use another function to do that, but those constructors are going to be matched on. If the constructors are not in scope, then you know that there must be some function exposed by the library. Either that T gets returned in the result in somehow without being touched, or you have some part of your library which consumes that. There's an interesting example in our standard library of something like this, which I've not looked at in a long time. I think it's called choice. So the choice data type says you have either an A or a B, but you don't have, they're both there, so you construct it by having both, but then you can only use one of them. So you can do choice AB to A and choice AB to B, which lets you use one but not the other. But like it's like they're both there and you can choose one but not both. And that's allowed because the module hides the constructor. So you can only use these two functions to interact with it. So once I've got one of these choice things, I can only read one part of it. So perhaps answers your question slightly.
It does. I mean, I've always felt a little uncomfortable by the fact that the answer to this question of what does it mean to use something once, the answer was always, well, it depends on what's in scope. I mean, that's sort of the answer I was expecting, but it feels somehow unsatisfying that what feels like should be a property of one specific function turns into, abstraction barriers and modules. And I mean, there's this funny thing that happens. I don't have any answer to it. I don't know.
I guess if you've defined your own data type, then the functions which a function which is linear in that data type, you know that it's got a pattern match on it. Like at some point it's going to be concretely matched on. There's nothing else you can do about that.
Yeah.
I can't. Somewhere in its sort of data flow chain, that's got to happen. If it's some kind of built-in thing like handles, then or something that's abstracted, then it's like, well, you have to use its interface, but operationally, well, that depends on what the operational meaning of those things are.
Yeah. Okay, that's good.
Thanks.
Dom, did you see Ruben's question? It was right above Richard's.
Yeah, that was just in response to the conversation about are the box with a single natural number, is that equivalent to the box with an interval? So you were showing some examples actually where the type system itself was doing some implicit coercion. You said one direction was fine and the other direction was above.
Right. Yeah.
Well, I'm just thinking.
But you could write the two functions explicitly, as you did in the case of an empty box and a box with one inside. Yeah. No, sorry. The unboxed linear type and the type of box with one.
Oh yeah. So write a function that goes from like box 2 to box 2 to 2.
Exactly. Yes, and the other way around.
Yeah. So there's a bunch of stuff about how we interact modalities that's in our ICFP paper.
Yeah.
But I've been kind of overhauling a lot of stuff recently, and I think a bunch of this is broken.
Yeah, I do too.
Like this.
Like that should
That's
work?
allowed. That should be allowed. I'm trying to think of the thing that is definitely bad. This. No.
No, the first one should be bad, right?
Yeah, that's no, the first one's okay because it's about over approximation. So 2
yeah,
becomes
okay.
2 to 2, and then you can over approximate it.
Yeah, you're right. Yeah, that's fine. Yeah.
I guess if this was 3, and then this said 2 to 2, that should be.
Yeah, that should not work.
Okay, that doesn't work. That's good. And the other way around would be like this, and that would also be bad. But if I made this 3 to 3, then that should be fine. Yes.
Will that work without the term level boxes?
Right, without the boxing, I think this is not going to work.
No, it's two different.
Oh, it does work.
Well, that should not work, right?
It's still just it's just sort of subtyping it, basically.
Oh, yeah, I forget we have subtyping. Yeah, okay.
Yeah, unless you do the approximation inside them when you're not.
Yeah.
No, I didn't have to do the boxing.
So the subtyping is doing the conversion.
3, 3, less 2. Yeah. Wait, why did I think that wouldn't work with this? Yeah, no, that's fine. Yeah. So what I want
because
to just do is this thing. And just see. Yeah, but I want to see the whole. Forgotten how to. Right, so here what's happened is we've got 2 levels of box. And what it's done is there's a sort of infrastructure inside that says, well, what do you do when you're dealing with multiple modalities that are underneath each other? So because these are 2 completely different things, what it's done is it's formed a product semi-ring of the 2 bits of information. So in scope here, we've got X, but it's graded by private and 2. But if this was like 5, well, I'm just going to put something here. Oops. Then what it's doing is it's multiplying, because they're the same. They're both natural numbers, and inside it says, well, you can flatten 2 levels of box for natural numbers by doing the multiplication. But if these were levels, let me have levels, L and J, then the flatten is actually the meat of the 2. So we worked out that was the right thing to do for levels. Like if it's private and public, then you end up with it being a private thing rather than a public thing. So there's stuff about interacting the modalities that way when you've got multiple layers, which can happen when you've got like data types with boxing inside of it and boxes on top. Yeah.
Yeah, and stay tuned for a killer paper on interactions between modalities.
Yeah, I mean, we have some stuff about it that we wrote in our ICFP papers based on this kind of flattening idea, which just does this. But there are some more complicated examples there where it becomes useful. Yeah, another interesting thing then would be what happens with this. It's something like that. And the answer here is that it converts this to an interval and then does the interval multiplication. Yeah. So Eric said, with regards to Richard's last question, you don't know the argument will be pattern matched during the execution of F, because F could simply return it, right? Yeah. So I guess you have to look at I mean, that's why parametrically polymorphic things kind of give you more information, because then you can tell when things are returned and not a bit more easily. Like if they show up in the return result or not, because then the type variable has to show up in the return result somewhere. So what would be super cool is to be able to generate lots of free theorems, like, well, more than free theorems, generate theorems from the types and then have access to them if you have like some dependently typed language, like have the type generate you all this other stuff for free. Because I think there's a lot of stuff you can get out of this. And yeah, that's another area for exploration, I think.
If the function simply returned the argument, then it wouldn't. You'd either have to make it non-linear, or you'd have to say it's used 0 times. So you get more information in the type of f there.
Well, if it returns it, then it's linear, right? Like this.
I see. Yes, it's used. The use is returning it. Yes, I see.
Yeah, the use is like showing up in the result. Yeah. Oh, here's something that's interesting I didn't mention. If you pattern match on a constructor with more than one argument, but it's inside a box, let me say it's like a negation. I can't make this box be 0. Are you going to write this program for me? Oh, oh.
Something went wrong.
What? Just open a different workspace. So I can't do true like this and say 0 because the typing let's go up here. It implies the unsatisfiable condition that 1 equals 0. So when we pattern match, it says, hey, this has to have at least one usage. So I could have one here. I have any other, I can have more usage than that, but let me go get rid of that whole. Or I can have, oops. Ignore holes, that's what I want. So here I said 1 to 10, that's fine. So as this pattern matching elicits a constraint that says there has to be, this grading has to be approximated by, sorry, it has to approximate 1. So it has to at least account for 1 use in it because you did the pattern match. Unless you have a data type which has only 1 constructor, then you are allowed to do this. Because it contains no information. Like a single data constructor has no information to it. It's just, there's just one thing that it can be. So for sort of mono-shaped data types, this is allowed. But for poly-shaped data types, things that have more than 1 value, then pattern matching incurs actual usage. This was a sort of interesting choice we thought we'd explore.
Are there any fundamental reasons for that, theoretical fundamental reasons for that choice or not?
We thought it was sort of information theoretic, really. It's like it's kind of completely, yeah, singleton elimination, as Eric has said. It's like you learn nothing from this value. You know it's got to be there. What's in combinatory logic.guru? Okay, I don't know. Is that one of our combinators and their types, SKI and CB.
Right. I thought there was maybe some interesting things in there about when you have more complex combinators or various combinations of combinators, can you say interesting things about them in the types that you can derive for them? But there you just have sort of some basic combinators.
Yeah, I think it basically just shows that there's a bunch of stuff that's linear, and K and S are not. So nothing terribly groundbreaking there, but just kind of writing them down just to check. I think we did think, oh, I wonder if there's anything interesting there. Not really. I mean, yeah. I mean, I don't want to say there's nothing interesting here. There's nothing interesting in this file. That doesn't mean there's not maybe something interesting about analyzing combinator complexity to do with data usage stuff, like different combinator sort of frameworks. Any other questions? Here's a library that shows you that map is linear by using the cost monad, grading monad.
All right. Well, thanks a lot, Dom, and everyone else for a great talk and a lively discussion. So,
Yeah.
Thank you.
Thank you, everyone, for the questions, and I hope the students as well found it interesting to sort of see what we get up to, and yeah.
Yes, thanks very much.
Yeah, thanks for coming, Richard. And if anybody has any interest in the other talks, check a look at the schedule and let me know. And
do feel free to download Granule, play with it, and submit bug requests or pull requests or anything. Yeah, it's open source and online. You can find us over here.
Yeah, for sure.
Great.
Awesome.
Take care, everyone.
Yeah, thanks a lot, Dom. I appreciate it.
Thank you.
Great talk.
Bye, everyone.